I
Go ahead.
I was like a little confused with also the on the like P imply something not something like that, and then the imply sign. I was
Okay,
can you show me the one more the talk table
sure,
using the like it was on the last quiz like that something.
sure. So on the last quiz, we were trying to decide if an argument is valid.
Yes, it says grow up in grace and then
All right. So let me grab that quiz and let's just work it through, shall we?
yeah.
All right, so this argument went like this. P implies R was the first premise. Q implies not R was the second premise. Therefore, not Q or R. That was the conclusion. Does that look familiar? So we have two premises. Everything above the therefore symbol is a premise. So we have two premises and we have a conclusion. So yes, in order to correctly evaluate this argument for validity, we need to be able to evaluate if P then R, and we also need to be able to evaluate if Q then not R. So we have to be able to generalize our rules for evaluating if-then statements. So we have a P and a Q and an R, and we also have a not R, all right? And we will have a not Q here in a minute. But first, I'd like to write the two premises. P implies R. Well, we already have the P and the R. We'll have those. And then we'll need to evaluate Q implies not R. We'll be able to do that with these two columns, the column for Q and the column for not R. And then we'll need to make a not Q column so that we can build the conclusion column, not Q or R. And then we're going to figure out rows of interest, and then we'll figure out if the conclusion is true or false in the rows of interest, okay?
Okay.
So we're going to need 8 rows. Under P, of course, we put true, 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 false, 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 false. Oh, I gave myself 10 rows. I don't need that many. I only need 8. And what goes under Q?
True, true, false, false.
Exactly. Good. And what goes under R?
True, false, true, false, true, false, true, false.
Okay. Fantastic. Let's go ahead and build the column for not R, and then we'll be set up to build this column. We can already build this column. In fact, if you like, we can go ahead and build this column first. So P is our hypothesis.
Mhm.
R is our conclusion. All right, you agree? And P implies R. If P, then R. So,
True.
so P is the hypothesis, and R is our conclusion. So we look, and if the hypothesis is true, we have to check to see if the conclusion followed. So in row 1, we have P is true and
Uh,
R is true. So if true, then true. What will that be?
true.
Good. In row 2, we have P is true and R is false. So what is the truth value of if P, then R?
False.
Exactly. That's the only time the if-then fails. It only fails if we have a true hypothesis and a false conclusion, whatever they look like. Okay, so good. Row 3,
True.
row 4,
Row 4 false.
good. And rows 5, 6, 7, and 8.
So I got confused. I think the false true. Uh,
Yes, when the hypothesis is false. So here the hypothesis is P, right?
yes.
When the hypothesis is false, the if-then statement is true by false hypothesis. Okay?
On the
Doesn't even matter what R is. Like it doesn't matter if R is true or R is false. The fact that the hypothesis P is
Mhm.
false is enough to make the if-then conditional true. Okay? So what happens in rows 6, 7, and 8?
The 6 7 is Paul 7 is false, and
No,
then
7 has P being false. The hypothesis is false. So what's the truth value of if
got
P then
uh,
R?
this true.
Good.
And the 6 I think I got like false is true.
False implies false is true. Good. And in
And
row 8?
true.
Exactly. In fact, rows 5, 6, 7, and 8 all have the hypothesis P being false. So the if then is true by false hypothesis in rows 5, 6, 7, and 8. Okay? Now let's make the column for not R, and then we can evaluate if Q then not R. Okay? So what do we put under not R?
False F true false true false true false and true.
Okay, great. So now Q is our hypothesis, right? And not R is our conclusion.
Yes.
So what happens in row 1 to if Q then not R?
You then it's false.
That's correct. Good. Row 2.
True.
Good. Row 3.
True.
By false hypothesis. Good. Row 4.
True.
By
Five.
false hypothesis. Excellent. Row 5.
Row 5 false.
That's right. It's the only time the if then fails is when the hypothesis, and this time that's Q, is true, and the conclusion, which is not R, is false. That's when the if then fails. Good. Row 6.
Row 6 true.
Good. Row 7
True.
and row 8.
True.
Exactly. So we've just made our premise 1 column and our premise 2 columns. We've got our premise columns sorted out, don't we? Now we're going to build our conclusion column, which is not Q or R. But before we try to build it, it's going to be helpful to build the not Q column, right? Because not Q is one of the components. So what goes?
Not Q, they're false. False. True.
Good.
True.
Yep,
False.
exactly.
False. True. True.
Perfect. All right. Now we're going to OR together not Q or R. So here we go. Here's our not Q and here's our R. So row 1.
True.
Good. The OR is true if either component is true or both. Good. Row 2.
False.
Excellent. Row 3.
True.
Uh-huh. Row 4.
True.
Uh-huh. Row 5.
True.
Yep. Row 6.
False.
Row 7.
True.
Good. Row 8.
True.
Excellent. So now we've got our premise columns made and our conclusion column made, and now we're ready and we've labeled those columns, premise 1, premise 2, and conclusion, right? So we know what we're looking at. Now we're going to identify the rows of interest. What are the rows of interest?
Uh, the last column, I think.
They're rows. Okay, so other column, they go across, they're rows. And they're rows in which all the premises are true, okay?
So there is the first one is true and the second one is false.
So that's not a row of interest. So we'll just not, right? So we can skip that row. What about row 2?
It's not. That's
Good. Row 3.
yes.
Yes,
It's
because we have 2 true premises. We only had 2 premises. If we had 3 premises, all 3 of them would have to be true, right? But we only had 2 premises, 2 premises. They're both true. So yes, this is going to be a row of interest. What about row 4?
no false. No,
What about row 5?
no,
Row 6?
and yes, all are.
Yeah,
I,
all the rest of them are rows of interest because both the premises are true and all the rest of them, aren't they? Great. So that's step 2 done. We have identified the rows that have all true premises. Notice we don't care about the conclusion yet. We're just looking for rows that have all the premises true, right?
yes.
Now we're going to go and in these rows of interest, we have 4 of them. We're going to check and make sure that the conclusion is true because remember, an argument form says if we have the first premise true and the second premise true, we only have 2 here, but we might have more. If all the premises are true, then this is a true hypothesis. And that's why we have to check for those rows where all the premises are true, and then we check for the conclusion. Right?
Yes.
So in row 1, look, here's our conclusion. Is it true or false?
True.
So far, so good. The conclusion is true, and everything is looking good so far. How about in row
It's a false.
6?
False.
Right. We have a false conclusion here. So the conclusion is false. That's going to make the argument invalid already, right? Even though the conclusion is true in all the other rows of interest, right?
Yes.
We have one row of interest with a false conclusion. So what do we decide? Now we're executing step 4. We're deciding. The argument is, you tell me.
Third one is invalid.
Yeah, because,
The row of interest, the 6, I think, is
yep,
false.
good. Be specific. We have row 6, a row of interest with all true premises or with all premises true. You can say it either way. It means the same thing when we say all, like that, with a false conclusion. And that's enough to make the whole argument invalid. Okay? So I hope that helped you with understanding how we evaluate if-then statements. You have to look at the hypothesis of the if-then, and you have to look at the conclusion of the if-then. And the if-then statement only fails if we have a true hypothesis and a false conclusion.
If then I'm writing not. If then
Yes, so here's the rule for evaluating. I'll use if curly A, then curly B. If curly A, then curly B only fails when curly A is true and curly B is false. Otherwise, if A, then B is true, including the rows where the hypothesis, curly A, is false. So here's a little do later exercise that I could give you to help you practice. Suppose if P then Q is false, determine whether each of the following is always true, always false, A. If Q then P, B, P or Q, C, P and Q, D, not P implies not Q, E, P, if and only if Q. So what we will use to work this is this. Here's the fact that will help us. If P then Q is false only when what? You tell me.
The when the P is true and the Q is false.
Good. And you can use those facts that we know now P has to be true and Q has to be false to help you figure out the truth values, either always true or always false for these.
And how about the E, the double imply?
Okay, so the rule for the biconditional, let's just go over that rule. Or I could say A if and only if curly B. I could use either notation. The rule goes like this. The biconditional. The biconditional, P if and only if Q is true when P and Q have the same truth value, whether they're both true or both false. Otherwise, P if and only if Q is false. Because remember, P if and only if Q means, by definition, this is the definition of P if and only if Q, it's that if P, then Q, and if Q, then P. Okay, so both of these have to be true for P if and only if Q to be true. These are both true if P and Q are both true, and these are both true if P and Q are both false. Those are the times when both of these are true, which is exactly what it means to say P if and only if Q is true.
And when the P imply Q and Q imply P both false, it is true.
Well, no. If P and Q are both false, then P implies Q will be true by false hypothesis, and Q implies P will be true by false hypothesis. So These are both true
Okay.
exactly when this is true because the biconditional is these two implications anded together. And these are both true when P and Q have the same truth value. But if P and Q have opposite truth values, one of these will be true and the other will be false. And that means the and operated statement will be false. And that means P if and only if Q will be false. You can build a truth table. Here's another do later just to convince yourself. Confirm the statement that P if and only if Q is logically equivalent to P implies Q and Q implies P using the rule the rules for evaluating the conditionals, the if P then Q and the if Q then P, the and the biconditional. You can check that this logical equivalence really works by making a truth table and comparing the column for P if and only if Q, where you execute this rule. This is the rule for evaluating P if and only if Q. Okay. And you can use what you know about evaluating if P then Q, and what you know about evaluating if Q then P, and what you know about evaluating an and statement to build up to this column and correctly fill it out. The column for this should look exactly like the column for the biconditional when you fill out the column for the biconditional according to this rule. Does that make sense? Try it. Okay, you can come back and we can even have an extra office hour this week if you want, and we can talk about it, okay?
Thank you.
You're very welcome. Other questions? I see we've got some. Hey, Darius, so good to see you in the office hour. I think this is the first time we've seen you in the office hour. So glad you're here. And Nora's here. Nora's here. So yay, we got folks here. So the first thing that we did maybe before you got here is we went over the quiz. Okay, so that's the first part of the video. If you want an explanation for the quiz 3 solution, okay? So we won't go back over that again, but it's going to be in the video. All right. And the notes will be in the office hour folder in Blackboard. And then these are good exercises to do later. And this one's a lot like a WebAssign exercise, I think, isn't it? I think you had a WebAssign exercise like this.
Quick question.
Yes.
Are the videos posted?
Yes, they're on YouTube. It's at Liz
Oh, I've been looking for them in
Atlas.
Blackboard. I don't see them.
Well, I'm so sorry, Darius. It's in the maybe I should put it at the top of the reading page, the link to my YouTube. But that's where all the videos are. And go to the playlists. And there's spring 25, 263 office hours. It says something like that. That might not be the exact name of the playlist, but it's close enough. It's at LizGoo 2766 for the videos. I'm so glad you asked. I'm sorry. Yeah, we discussed that on day 1. It's in the syllabus, but I should probably post that at the top of the reading page. I can do that. Other questions?
Evening, Professor. I had a question about the special homeworks, the most recent one and the one before that.
The measure two material, good.
Yes,
Did you see that I arranged it by chapters because we were getting so many of them?
yes. And
So
I was able to, I'm sorry.
go ahead.
No, I was able to look in the textbook and get some more information about circuits.
Good. So were you able to work the section 2.4 circuits and Boolean expressions worksheet number 1?
Yes, I did. I did all of the questions.
Okay, and the
And
solutions are there.
yes, I saw the solutions. I just had a question about using the full adder when you are carrying and you have three variables, then that's the time to use the full adder.
That's correct. So on the worksheet on building circuits for binary addition, so this is in the measure 2 material folder, and everybody should be working through all of that measure 2 material just as diligently as you would do if you were turning it in to be graded. That's also in the syllabus. So the chapter 2, it's the worksheet on circuits for binary addition. So would you like to work through? I haven't posted the solutions to those, but I can do it here.
That would be great.
All right, so shall we start with number 1?
Yes.
So this is a nice, simple one. Design, or, I think I say design or build a circuit that will add PQ plus RS. Use full and half adders and show work. And I'll show you what I mean by show work. We always want to show the actual addition work. So the work I'm gonna put over here on the right. So in order to have room to show work, I'm just going to space these out a little bit, just in case I need room. Okay. So we always start in the rightmost column when we're adding. This is the 2 to the zeros column, the ones column. And then once we're done with the ones column, we'll move to one column to the left. That's the 2 to the ones column, and we'll add those. And if there's anything over here in the 2 squared column, the fours column, we'll add those. So we look in the 2 to the 0 column and we see, oh, we've only got 2 digits to add. So we're going to add Q and S. And what kind of adder do we need to add Q plus S?
A half adder?
Yep, so I'm just going to kind of make it skinny like this. And I probably shouldn't have used an S, but it's okay, because out's going to come sum 1 and carry 1. Now let's look where sum 1 and carry 1 go. I don't really need this line all the way down here. Well, sum 1, the sum digit, always stays in the column with the digits whose sum generated it. So we added Q and S and we got the sum, and there aren't any more letters in this column, so that's the final digit for the 2 to the 0 column. The carry goes one column to the left. So the carry is going to be in the column with the P and the R. So that means now we're done with the 2, this is the 2 to the zeros column. We're done with that column, the ones column in binary addition. But now we're going to add C1, P, and R. Well, here's the wire for C1. So now we can put the input for P and for R. Notice we don't put PQ first. we put QS first because those are the first ones we're adding. So we don't put these in alphabetical order now. We put them in the order that we need to put them to perform the addition. So P and R are going to get added to the digit C1, which is in that column. This is the 2 to the 1s column. The 2's column, the 2 to the 1's column. So what kind of circuit do we use to add C1, P, and R?
A full adder.
We do. So we'll draw a full, we'll just write full in there. And it's going to output sum 2 and carry 2. Well, sum 2 is going to stay in the column with the digits that generated it. And there aren't any more digits there, so it is the final digit in the 2 to the 1's column. Carry 2 is one column to the left. And you could put it here or here or here. I'm just putting it here. And that means carry 2 now. And so we're done with sum 1. It's there. We're done with sum 2. It's a final output. And now there's nothing to add to C2. It's just a 0 here, even though we don't write it. So we just bring the C2 down. And that is our final digit for the 4's column, the 2 squared column. So that's what it looks like to show work. All right, so now let's look at the next one. Now, I think I gave y'all kind of an interesting problem at the end of class, too. More interesting than either of these. We can do that one, too. But the next one is to add same directions as number 1. And I'll just go ahead and write it over here. We're going to add P, Q, R plus S, T, U. So what would be our first input wires that we would draw?
R and U.
Yep, and I'm going to put them over to the side a little bit because I know I'm going to need a little more width here. R and U, what do we add? Because they're in the rightmost column, they're in the same column, they're in the 2 to the 0 column. So what kind of circuit do we use to add those?
A half adder.
And what's the output from that?
C1 and S1 and C1.
Yep.
Does it matter which one goes on top?
It doesn't. If you put the C1 here, you'll just have to cross the wire over the S1 wire or bring it out further.
Okay.
It doesn't matter. But I knew that S1 was going to be a final output digit, so I put it on top just to leave it out of my way, but it doesn't matter. And how do we know that S1 is a final output digit?
We put it underneath RU.
That's right, and there aren't any more digits in that column. Now, where does C1 go?
C1 goes above Q.
That's right, it goes one column to the left of the column containing the digits whose addition generated it. All right, so we have C1. Now, what are we going to add to C1?
Q and T.
So we'll put in Q and T input wires. And now we're going to run Q and T and C1 through a circuit. What do they get added with?
A full adder.
They sure do. So, and what should be our output from that?
S2 and C2.
Good. All right, let's go over and show our work. Where does the S2 belong here?
Underneath T.
That's right, because the sum digit stays in the column with the digits whose addition generated it. And S2 was generated by C1, Q, and T being added, so it stays in that column. And where does the C2 go?
Above P.
That's right, it goes one column to the left of the column containing the digits whose addition generated it. So now what should we do?
We need to input P and S.
That's right, P and S. And they're in the same column together with C2. So we're going to add those together. We always add digits that are in the same column together, just like we do in decimal addition. And what does it take to add 3 digits?
A full adder.
Great. What will our output be from that operation?
S3 and C3.
Where does the S3 go when we're showing work?
underneath the S.
Good. Where does the C3 go?
It's next to, yeah, it gets the next column.
Yep, and that's going to be the 2 cubed column. That's the H column. Just like in decimal, it's the ones, the tens, the hundreds, the thousands, powers of 10. Well, when we're doing binary addition, it's the ones, the twos, the fours, the eights, the 16s, it's the powers of 2. And now what happens?
We drop the C3 down
That's right,
and
because we're adding it basically to 0. So the S2 is a final output digit, and the S3 was a final output digit, and C3 was a final output digit. You don't have to circle these, but it can be helpful. And there they all are. Now, I think I left y'all with sort of a complicated problem, a do later problem at the end of class. Shall we look at that one?
yeah.
All right, can you, I don't know that I've posted those class notes yet. I should do that. Can you look at your notes and tell me what that do later problem was?
Yeah.
So this is the shorty version of the instructions. Okay, we're going to add them, we're going to show work, and we're going to build the circuit. All right, so what are we adding?
Okay, I think I found it.
Thank you so much. I got to dig those out and take a picture of them and post them.
Okay, it was the first row was X, Y, Z, W.
So our first number has it ones, twos, fours, eights. So it's got 4 digits in binary. So X, Y, Z, W. All right, what were you adding to that? What's the next number?
The next row is T, U, V, R.
So I'm going to skip a line in case I need room. T, U, V, R. All right, what's the next number?
And then the next one is only 2 digits. It's Q, N.
All right, and there was one more.
It was P, M.
All right. So as usual, we're going to start in the ones column. How many digits are the maximum number of digits that we can add together?
3.
So what should we do first? Start at
And, sorry.
go ahead, we'll start at the top.
Add W, R, N.
So I'm going to input W, R, and N into our circuit. What do we add them with?
A full adder.
All right. And I'm going to try to make this narrow because this is going to take some room. All right, what's our output from that first adder?
S1
Uh-huh,
and C1.
great. And I'm going to offset them a little bit because I see something coming. In our work, where does the S1 belong?
It goes above M.
That's right, because it was generated by adding W, R, and N. So it's right here. We still have to add it to M. So if you want, you can kind of cross these out. We've done those, right? You don't have to, but you could. Where does the C1 go?
Above Z.
Yep, and I'm going to move this because we're going to need some more room. I can tell you right now. C1 goes here. So we are not finished with this first rightmost column because we still have some digits above the horizontal line that need to be added. So what should we do next?
We add S1 and M.
So I'm going to bend the S1 wire down and then just bend it a little to the right. And we're going to input the M wire. And what should we run those through?
A half adder.
Yep, we're going to run them through a half adder because it's only 2 digits. What are the outputs from this adder?
C2 and S2.
And in our show of work, where do these digits go?
S2 goes under M.
That's right. It stays, the sum digit stays in the column containing the digits that generated it. What about the C2?
C2 goes above C1.
That's right. It goes one column to the left, and I'd just like to stack them. All right. So we have a final output, S2, but the C1 and the C2 are not final outputs. So, but we are done with the 2 to the zeros column. We've added all the digits. And now we can move over to the 2 to the ones column. So what should we do? I like to just start at the top and make my life easy.
So we're adding C2, C1, and Z.
All right, so here's C1's wire, here's C2 wire, and here's Z's wire. What do we add those with?
We add them with a full adder.
Exactly right. So we're going to draw a little skinny full adder, hoping that this is all going to fit. And what's the output from that addition of C2, C1, and Z?
C3
Uh-huh.
and S3.
Okay, so there's going to be a C3 and an S3. Now, in our show of work, where does S3 belong?
S3 is above V.
Yeah, it's in the same column with the C2 and the C1 and the Z, because that's what generated them. What about C3? Where does it belong?
Above Y?
That's right. It's one column to the left of the digits C2, C1, and Z, because it's the carry. It always goes over one to the left. Now what should we do?
Now we add S3, V, and Q.
Oh, this should be a 3, my bad. S3, V, and Q. Good. So here's the S3 wire. Now we make V and Q wires coming in as input. And we're going to run S3, V, and Q. We're adding S3, V, and Q. And what will we run those through?
A full adder?
Absolutely, because it's 3 digits, requires a full adder. What are the outputs from that?
S4 and C4.
Good. S4 and C4. Now in our show of work, where does S4 belong?
S4 is above P.
Right, because S3, V, and Q were added together to make the sum digit S4, and C4 will put one column to the left. I jumped the gun on you. Great. Now what?
Now we
we're
add,
oh. Yeah, I'm just going to say this, we're going to stay in this column until we're completely done with this column. All right?
so S4 and P?
That's right. So we're going to bend S4's wire and run it with P through an adder. What kind of adder do we need?
A half adder.
That's right. We need a half adder for those. What are the outputs?
S5 and C5.
S5 and C5. Good. Now, so we just added S4 and P. So where do our output digits S5 and C5 go?
S5 goes under P.
That's right. It's a final output digit. So far, S2 and S5 are our only final outputs so far. Where does C5 go?
C5 goes above C4.
That's right. And if you wanted, you could put it here. It's okay. I like to stack them, but it really doesn't matter. As long as it goes in this column, anywhere will do. Okay? Just FYI. Now what do we do?
We add C5, C4, and C3.
That's right, because we are done with the 2 to the ones column. We've added all the digits there. So we're starting on the 2 squared column. So C5, C4, and C3 are there at the top. We'll go ahead and add them. But again, it wouldn't matter if we sprinkled them around. C3 could be there, and C4 could be here, and C5 could be under U. The point is, these are all in the same column. So but let's go ahead and do this. So we need to find the C3 wire. Here's the C3 wire. And the C4 wire. And the C5 wire. I'm going to make it a little shorter so that we can run all those carries through an adder. What should we use?
A full adder?
Yep. And what is the output from that full adder?
C6 and S6.
Great. C6 and S6. Where do those output digits go?
S6 goes below Y.
Yeah, we can put it, as long as it's in the same column, it's fine. You know, if we had room here, we could stick it here, but the point is it just needs to stay in this column until we deal with it. What about C6? Where does it go?
C6 goes above X.
Because we have some room there. Great. Now what do? We've just added these together.
We add Y, S6, and U.
That's right. So we have the S6 wire, and now we're going to input Y and U. And what do we add those with?
A full adder?
Yep. And what is the output from that?
S7 and C7.
And I'm going to put the S7 over here out of our way because I know something's happening with that. And here's the C7. So where does S7 go in our work?
S7 goes beneath the line under U.
That's right, because we just added Y and S6 and U to create S7. That is one of our final output digits. We're done with that column. Where does the C7 go?
C7 goes above C6.
That's exactly right. We're getting there. All right, now what do?
We add C7, C6, and X.
That's exactly right. So here's our C6 wire. We'll just bend it down. And here's C7 wire. And we need X. And it's 3 wires, so we run it through a full adder. What is the output from that? From adding C7, C6, and X?
We get C8 and S8.
C8 and S8. And where do they go in our work?
S8 goes above T.
That's right. No, it has to be somewhere in this column with T. And what about the C8, the carry?
C8 gets the next column.
All right, I'll just stick it there. Now what?
Now we add S8 and T.
We're finishing up the 2 to the 1, 0, 1, 2, 3, the 8's column. We're finishing up the 2 cubes column. So it's S8 and T. Oh, we have just barely enough room. S8 and T. So what do we use to add S8 and T?
A half adder.
And what is the output from that?
S9 and C9.
Oh boy, S9 is a final output digit. C9, we're going to have to deal with. Where does S9 go?
S9 goes below the line beneath T.
That's right. It's the last thing that's happening in that column. And C9 goes, you know, somewhere over here in this column. It doesn't matter if it's above or below. Now what do?
We add C9 and C8.
Okay, here we go. Let's see if Dr. Good can do it. Here's the C8 wire. Here's the C9 wire. Oh man, it's just barely going to fit. I'm going to put the output this way. It's cheating. I don't like to do it, but I'm going to do it. What's our output there?
S10 and C10.
Yeah. So these often have to be done, you know, in landscape mode, but we made it. And this was a half adder that added those two carries. All right, so in our work, we just added these last two carries here. Where do our outputs S10 and C10 go?
S10 goes below the line beneath C8,
Good.
and C10 goes to the left of S10 below the line. Oh,
Yep.
it goes
Yeah,
up
and
there.
that's fine. I wouldn't take off if you just went ahead and put it because you know you're done at this point. These are our last two output digits. And I should put a circle around S9 to be consistent. And that's how we do it. And I can raise this up a little bit so you can see the whole thing a little better. You can almost see the whole thing. Kind of hard to see the whole thing. But here's the circuit. And like I said, I mean, I should have, right? Like here, I was a little too generous. I should have made it a little skinnier there. It got skinnier and skinnier and skinnier. And then here's our work with all these carries and sums. Some stay in the column with the digits whose addition generated them, and carries always go to the column to the one column to the left. And that's exactly right. And that means we used 10 adders, because if we're indexing all the way up to 10, it had to have taken 10. Couple things to check when you do this work yourself. The output from any adder has to be two digits, a sum and a carry. They will never be added together because they are never in the same column together. And they will always be indexed with the same number. If you come to an adder and you've got like an S3 and a carry 4, you've made a mistake, because the output from any of these adders is two digits that are indexed the same, but that never get added together because they're always in different columns. Good job.
That was really interesting.
I'm glad you enjoyed that. Very good job. Other questions? Now we have complete solutions to both that worksheet and to the due later problem. It'll be nice to post these. And I'll send out a little announcement and let people know that they should check the office hour video.
Will circuits be on our test?
Sure. We spent a lot of time on it. We might as well. I think circuits are really interesting for computer science students because it's really where the rubber meets the road. Suddenly, it's not theoretical. This actually works. Like if these are binary digits. These are either O's or ones. And if we had numbers like this, we could run them through this and get the correct carries and sums. And you have some WebAssign that asks you to do that. Then we'll get the actual correct answer. So this is when a circuit really does something that's not just theoretical, it's very real. We have to be able to add numbers. And it's a good first test for any computer that you're building, is check and see if it correctly adds binary digits. Other questions?
Will we be tested on logical equivalences specifically?
Using the rules of logical equivalence, no, but I may give you two circuits and ask you if they're logically equivalent, and that would mean you would have had to construct their I/O tables and compare. I might give you two logical expressions and ask you to use a truth table to discover if they're logically equivalent. But that table of logical equivalences with all the different rules, you don't have to worry about memorizing those.
Okay. I was worried.
Yeah. No, actually, if I was going to ask you to do that, I would give you that as a reference sheet. So I wanted you to get some experience with that just so that you can understand there's more than one way to approach it. But for us, for our purposes, being able to compare IO tables or being able to compare truth tables will be the method that we use to determine if two circuits are logically equivalent or if two statement forms are logically equivalent.
Quick question.
Yes.
Has there ever been an instance where the output for a circuit ends out to be like an AND rather than an OR?
That's a really good question. Let's think about what these binary digits mean. A 1 instead of an O? Or did you say an N instead of an O?
Yes, because I know an OR at the end, which is where the output is usually going to be either a 0 or a 1. But if it is an AND,
Well, N could be
has there
O or
ever been
1.
any instance where, the output would come out that way?
We will always have outputs that are O's and 1s, but it is interesting to look at that rightmost digit. For example, we knew that adding O plus O yields OO, and adding O plus 1 yields O1, and adding 1 plus O yields O1, and adding 1 plus 1 yields 1, 1. But if you go back and look at the notes, and if you understand that this is the 2 to the 0, or the 1's digit, and this is the 2 to the 1, or the 2's digit, you can see what these numbers, oh, this should be a 1, oh, my bad. 1 plus 1 plus 1 is 1, 1. If you think about what these binary numbers actually mean, and again, we did this in the notes with a fairly long number.
Professor, can I just ask really quickly, when you did the 1 plus 1 plus 1 and you put down a 1 and carried a 1, that was because of the sum would be that you would have a 0 after 1 and 1, and you would add that to 1 and put it down.
That's exactly right.
Okay.
If you perform this with, and if you look at our circuit that is a full adder, it's you use a half adder to add 1 plus 1, and then you use a half adder to take the sum digit from that and add it to this, and the two carries can't both be 1, so we use an OR to get the correct carry, but you could use a half adder, it wouldn't be efficient. But the point is we have a carry from adding this 1 plus this 1, and then we have a carry from adding the sum digit that is output from that addition to this 1. So there are two carries over here. So you can look at
Okay.
that circuit. But it's interesting if you realize what these numbers really mean. O in base 2, well, that's O times 2 to the 1 plus O times 2 to the 0, because we don't have any 2 to the 0s, and we don't have any 2 to the 1s. So this is 0 in base 10. But O1 in base 2, well, it's and maybe I should write this in the other order. Maybe I should do this in the opposite order. It's 1 times 2 to the O plus no copies of 2 to the 1. And that is just 1 in base 10. You go back and look at, and so what is it? What is 1, 1 in base 2, really? Well, it's 1 times 2 to the O, because we have a 1 in the 2 to the O's place. And we have a 1 in the 2's place. So it's 1 plus 2, and that's 3 in base 10. 1O is 2, right? Because we don't have any 2 to the O's. We don't have any 1s. But we have 1, 2. 1, 2 to the 1. I mean, so 1 plus 1 really is 2. This is 2 in binary. This is 3 in binary. And remember, we did a long one. Like, I think we did something, I don't know. I'll do one for you. I mean, does that number really represent in base 10? Well, this is the 2 to the O's place. This is the 2 to the 1's place. This is the 2 squared place. This is the 2 cubed place. And I had to choose what I was going to teach. I could have taught binary addition, or I could have taught circuits. And I just don't have time to do both. But it is interesting to do some reading in the book because they teach you how to add binary numbers by hand. But it is certainly helpful to understand, this is a 12, what this number, base 2, really means. Let's look at it. It's 1 times 2 to the O. By the way, if a binary number ends in a 1, it's going to be an odd number. See, this ends in a 1, it's an odd number. This ends in a 1, it's an odd number. If a binary number ends in an O, it's an even number. Why? Because if you have a 1 here in the 2 to the O's place, all these other digits represent powers of 2. They're all even. And then you're adding a 1 to that at the end. And that's why you get odd numbers if your binary number ends in a 1. So that might address your question. If a binary number ends in a 1, it's an odd number in base 10. If a binary number ends in an O, it's an even number in base 10. So we have 1 copy of 2 to the O, which is a 1, because 2 to the O is 1, plus 1 copy of 2 cubed, so plus 8, plus 1 copy of 2 to the 5th, so that's 32, plus 1 copy of 2 to the 9th, that's 512, plus 1 copy of 2 to the 11th, and that's 248, and 1 copy of 2 to the 12th, which is 4096. So this is 1 plus 8 plus 32 plus 512 plus 2048 plus 4096. You see what I mean? Except for the 1, these are all powers of 2. They're always even. So if you have an even number and then you add a 1, you're going to get an odd number. If there was a 0 here, you wouldn't be adding a 1 to a bunch of even numbers, so the sum would wind up to be an even number. Does that make sense? In base 10.
Saw the binary addition in the textbook, and it went on to talk about binary subtraction, but I was not able to understand where the carry number is coming from.
It's